Okay, fixed audio maybe. Problem 18. An automobile having a mass of 1,250 kilograms is traveling at 40 meters per second. What is its kinetic energy in kilojoules? How much work must be done to bring it to a stop? Alright, so we got the concept of braking and energy being converted from kinetic energy into heat. So let's first calculate its kinetic energy, and then that's the moving state, and then the final state is when it is stopped. So solution, there are two. The automobile is in two states, moving and stopped. The moving state has a kinetic energy that can be calculated via, then we'll use that same equation, which is E sub k is equal to 1/2 mu squared. The stopped state has 0 kinetic energy. How much work must be done to bring it to a stop? Interesting question, but I think it's just asking. Therefore, let's see here. Because there's a few ways to go about this. Therefore, work injected into the system to slow the automobile must at a minimum be greater than or equal to the kinetic energy already present, I think. Well, I guess it depends on what's doing the work. Automobile brakes, when they do their braking action, they're bleeding energy from the automobile into the environment. So therefore, the automobile must lose energy. It may do this by performing work on the environment. This may be done by the automobile brakes, which convert kinetic energy into heat energy. Kinetic energy of the convert the vehicle's kinetic energy into molecular vibrations of air in the environment. Which I guess you could say is work that the car does to the environment. So let's calculate the kinetic energy. The kinetic energy of the automobile is, we'll go ahead and insert several equations. E sub k equal to 1/2. Let's take those dots out of this. times the mass. Mass of the automobile is what, 1250? 1250 kilograms times the velocity squared. The velocity is 40 meters per second. 40 meters per second. We'll square that. Be this mess. Which is equal to joules already. We've kind of shown before. And that is equal to 1250 times 40 times 40 divided by 2. 1,000,000 joules. So a megajoule. Okay. The kinetic energy of the of the moving automobile is 1,000,000 joules. Oh, in kilojoules they wanted. Alright. So for every 1,000 joules, you have a kilojoule. .1,000 kilojoules. Great. How much work must be done to bring it to a stop? Yeah, so must be done. It doesn't actually talk about what is actually doing the work on what, but I'm saying the automobile is working on the environment. So the environment working, yeah. The automobile is a heater for the environment. That's the work it's doing. It's heating. And if you convert all the kinetic energy into heat, then yep, that is the work done. And it's going to be 1,000 kilojoules because that's the kinetic energy available to do the work. At 100% efficiency, I guess. I guess you could do some weird thing with the 40 meters per second and say, if you decelerate at a certain rate, how long will it take? Then you take that rate, let's see. Could you do a force calculation? Force times distance? I guess you could. But, ugh. Yeah, I don't want to do that. No, thank you. This is good enough for me. Okay, that is problem number 18. The brakes must dump. So the brakes act as, or the automobile brakes act as a heater. Act as a, maybe thought of as, the automobile brakes may be thought of as heaters that heat the environment. Heaters whose work is to heat the environment. The work maximum by converting the automobile's kinetic energy into heat energy. The total amount of kinetic energy available to be converted is 1,000 kilojoules. Therefore, the amount of work performed on the environment by the brakes in bringing the automobile to a complete stop is the same amount. 1,000 kilojoules. Done and done. I'm happy with that. Is that everything? I think so. That's number 18. Let's see. Problem 18 answer. All right, save that, export to PDF.